Hi everyone, good afternoon or morning. My name is ADITHYA MURALI and I'm going to be talking today on deep neural networks for automatic recognition of food and drink images. Feel free to stop me anytime and then ask me more framework related questions if you're more technical. I'm going to explain this like a little bit of story and basic case study and build some motivation first of all. Like why build AI for recognition of images, especially food? Well, it turns out that people are becoming increasingly aware of the importance of a healthy diet. And that basically creates the need for automatic food and image recognition. AI in food and image recognition basically offers epicures and snackers like me, like ability to make smarter and like more conscious nutrition decisions. If you talk to like nutritionists at Kaiser, they kind of recommend patients to install and actually pay for apps like MyFitnessPal. And it allows them to log food intake and create recipes and organize that. Fitbit offers something like that recently now as well. But as researchers in UCLA School of Medicine kind of confirmed, even though these apps are pretty useful for very fit individuals, patients that are overweight, it doesn't result in increased weight loss. And it makes sense because furthermore, like the patients stopped using it completely because it's too tedious and they already had stressful and busy schedules. So we asked the question, can AI help us eat healthy? Which is like the subject of the talk. And what we ended up doing was build our own image recognition service using TensorFlow and lesser known libraries like Surprise, etc. on Python on the cloud. And I'm going to call this experiment 1 because by the time we finished that project, some cloud vendors already started exposing some of their image recognition services to the public. And these don't require training, they'll just go ahead and spit out some labels. So we got some data analysis interns and specialists from UCSC and Syracuse University and gave them a challenge. Hey, go ahead and benchmark our service against other leading image analysis services. They chose to benchmark against Google Cloud Vision, AWS Recognition, and Microsoft Computer Vision. And I'm really sorry to do this. You're going to see a lot of food images right before lunch. So,
we're hungry.
So the interns basically scoured the internet and got 517 labeled images from ImageNet, which is a database of food images from different cuisines, and basically that's the URL, and the entire URL is part of the article on our website as well. And one thing they also did was they were careful to convert all the raw image format into, again, food images, into JPEG, and also like 640 by 480 pixel dimension. So the benchmarking is standard against all these services. And some of the immediate challenges we found, even the interns found, which obviously we would design also knew about, were that exact label classification is very difficult due to nature of food and drink items. This is actually one of the reasons called convolution neural networks. And what I'm trying to say is like, there was a question between deep learning and machine learning, and I wanted to keep that conversation here, reiterate that question again here. So machine learning usually, you mentioned there's features defined, and you go and try to build models with it. One of the use cases for deep learning for image recognition is actually from raw data. So you're trying to, you're not building a feature space. You're trying to go directly from raw data, and that's why there's an application of deep learning here, right? And what you'll notice is food itself is a very deformable object, which means you can't get defined structures from it. Some key aspects, whether from the designing end as well as in the analysis end, you'll see that factors in the image, like properties such as color, lighting, food density, like how much of the food is in the image, all play into factor in classification and later evaluation. So, for example, well, compared to traditional approaches, people try to approach image studies using machine learning, traditional machine learning approaches also. And what it turns out is deep learning has overcome some of these obstacles. And as we will show, it gives you precise on-the-mark labels for certain images. And for example, pan-fried pork dumplings, one of the CNNs kind of gave back a result with a label called dumpling, which is pretty much a generic dumpling that's on the mark. You're never going to see the complete text. The next challenge is correct label classification becomes very difficult, not only from a design perspective, but also from an evaluation perspective, because multiple labels become acceptable. In the image pan-fried pork dumplings, you got labels like dumpling, but if you notice momo, gyozi, mandu, and pierogi, I'm going to butcher some of these names, but also mean pan-fried pork dumplings, but it's just in different cuisines or different regions in the world. So how do you classify them as acceptable? You could try to run through a translator, let's say, right? And you can, for example, mandu or pierogi might come as dumpling. But gyozi, just like other ethnic cuisines, has now a dictionary, has a word in the English dictionary. So a translator is not going to translate it, it's just going to send it back to you. So, and also some of these images they collected were labeled in other languages, like in French, Italian, because they were from different cuisines. So how would you set up a study for that? It was also a challenge. So there were a couple of ways they approached evaluation. One was an automatic mechanism. So that way, they wanted to use an approach where they can automatically gauge all the services, but also do a manual approach of going and curating all the labels anyway. So one of the ways to do, so basically, for each image that's correctly labeled, you got a list of output labels. And you got this for each service, right? So what they did was, they used Levenshtein's distance, which is a measure of similarity between two strings. And Levenshtein's distance is pretty good, and it's better than Hamming distance or some other types of evaluation metrics you may have heard of for other reasons. It's because Levenshtein's distance is basically, in the example kitten sitting, is going to be like the number 3 because it's going to see how many edits it will take for one word to become another. It's not a similarity, search. So in this study, we use some libraries in Python, and you get a normalized Levenshtein distance score and consider a score of more than 0.9 essentially as the correct label. So in this case, none of these labels would have actually passed that threshold. And what the interns went with was, they called this a heuristic classification. Because again, the reason it's heuristic is because it's a barometer on how well all these services do. It doesn't really investigate each label as per the challenges indicated earlier. And what they found was, if you perform this Levenshtein's distance score and you keep the threshold at 0.9, images with having those kind of labels out of the 517, Microsoft Computer Vision got like 8 images precise, AWS around 11, Google around 78, and our Instagate's about like 219 images. With that, they went on to manually look at all the labels outputted. And the way they classified labels as acceptable or no is basically, they'll take, so in the case of pan-fried pork dumplings, they'll say it's dish. This is too generic of a label. This is prepared cuisines, if you will, right? So that's not an acceptable label for any food image. In fact, all food images is going to result in that labeled dish. But gyozi, dumpling, momo are yes, because they mean pan-fried pork dumplings in other languages, and so on and so forth. They, after manually curating all of those with a couple more interns actually, they ended up getting a label precision score across all of the services. And at this point, you'll notice that not all services generate the same amount of labels. I can't speak to how people tweak their CNNs, but for example, Google tends to, for the 517 images, ended up throwing out about 5,700 labels. That's at least, again, maybe 100 labels-ish per image, right? Amazon around there, but Microsoft had only 3,000. So we kind of did a percentage score, and Instagates gave only about 1,300 labels because it's more of a specialized AI, which solves something in your slide earlier. So basically, like, based on precision score, we got about nearly 80%. Well, Microsoft was about like 3%. And we went to a most important metric, the image precision. This is what they decided as, hey, it doesn't matter if Google gave more labels than every other service. We're going to say if any of those labels for an image was acceptable, we're going to say that service got that image right. So although you can see there's going to be a little bit bias towards Google and AWS here, it roughly comes around like image accuracy around like 68% for Google, 20% for Amazon, 13% for AWS, around like 84% for Heuristic Specialized AI. One of the key things to note is keep that precision difference score between Google and AWS. Because it kind of made me look at this example a little twice, look at this result a little twice when they presented it, because it makes no sense why Amazon would be so far behind on Google, but there could be some interesting reasons behind it as I go forward with the slides. So initial final thoughts were that for image recognitions they used, they benchmarked everything, Google, Amazon, Microsoft, and others, and we found out that domain agnostic standalone convolution neural networks tend to not perform well in food and drink image because of challenges reviewed earlier. So your agnostic AIs are still not at the level yet compared to specialized AIs if you train them for a specific purpose. And we do have some additional ML layers on top of our CNN, which is also customized, so we have sometimes more precision than other services. But there's one question that I asked is because these images that they used were all from ImageNet. So I asked, is there a bias by benchmarking these image recognition services using images from ImageNet or Internet? Because if I actually Google image search, pan-fried pork dumplings, I'm going to see that image at exactly that they ran pretty soon. I'm not going to see it in Bing, unfortunately, but maybe that's why Microsoft is so poor. Right? So some of these deep neural networks might have been trained on the test data set that they ran against. Right? So, and Amazon is not in the search engine space at all. So maybe Google had this edge. So that brings us to the second experiment. So they got, with consent, about 100 labeled images from food from different cuisines not found on the internet. They were taken on the smartphone from people and they kind of get consent for it to be in the database. They curate it down. It's either using an iPhone or an Android phone. And basically, this mission was to compare these deep learning services. They did drop Microsoft's Vision service for another specialized AI called Clarify AI, which is also a food-based AI. And they want to compare basically which deep learning image service is most capable and precise in detecting the food label. So same thing. These are some of the images from the new data set. And they run it, again, by converting the JPEG format because both iOS and Android are proprietary formats. Ensure they're JPEG before they run it through all these services. And a couple of quick observations is that, okay, so it may not be the best image, but you'll see right here that in our previous study, we tested Google Vision API with the cheese pizza taken from the smartphone on the left. And then this is the cheese pizza taken from a smartphone, from the internet on the left and the smartphone on the right. Is it a little bit clearly visible? So this is interesting because from the internet, Google gave a confidence score of 95% is cheese pizza. I know it is cheese pizza, there's no way. But, I mean, it's not, it's deformed. Food is a deformed object. So the second cheese pizza, Google had no idea what it was. And it has to do with the fact that there's extra lighting on images over there, and also it has to do with ImageNet itself. Because if you look at the rules of which ImageNet accepts images into its database, they need lighting. They don't need obstacles. If you submit an image with an obstacle in it, or two different items, they won't accept it. So if you have your entire CNN kind of trained on for example, you might have a fork next to your food item, and Microsoft tends to say fork. And if I look at all the labels, it's like fork, spoon, because it's so focused on one of the object, not the other object. So these are the challenges actually, what will happen if you go ahead and start just straight up training your TensorFlow on ImageNet data. There's some tricks to this. There's boosting, your traditional machine learning techniques need to come and play here. But you can see here that from this example, and there we had like several more examples that Google was not able to pick those up. And with that, I just want to look over and give you a quick evaluation. And I want to show you more complex document of what's acceptable or not acceptable. This is an example of chicken pho on left and the definition on the right. So this is one of the things that a bunch of data analysis people create like a document, because it becomes very ambiguous, and sometimes a user might say a label for an image is acceptable when another user may not. So one of the evaluation metrics they said is, hey, if a variation of the word or if it's part of a definition, is an acceptable label. So for example, for chicken pho, as well as noodle soup were acceptable, but if you just said soup or Chinese noodles or dish, is not acceptable because that's way off the mark. And it was important to train every data analysis, and kind of like we did kind of like an averaging score, so we get the most accurate results. And what you'll first notice is everybody, including Instagates, took a huge precision hit when you start using real-world images. So none of these 50-60% accuracies anymore. And actually, you'll notice that Clarify AI, which is one of the specialized AI, is not doing too much better than Amazon Recognition. And it's actually doing poorer than Google because I mean, you can say anything, but Google has trained pretty much its data on its entire, on all of ImageNet and basically all of its indices also, because it kind of uses a Google images index to recheck the images. And you can actually see that in the output from Google, so what they're doing there. So essentially, it turns out Clarify AI gave the most amount of labels, close to 2,000. AWS Recognition gives the least amount of labels, which is a clear switch when you compare that with Instagates in the previous study. We ended up getting more labels as well, but in terms of precision, Instagates was still declaring around like 14.3%. And image precision rate, there were about 100 images, and again, the most important factor, because this is what your workout plans or your nutrition diet is what a nutritionist at Kaiser or somebody else is going to recommend on, based on how correctly you have tagged your food that you've eaten. And it turns out here, like, Instagates was about 85%, we got about 85 of those 100 images right. Clarify got a little bit better, even though its precision was lower, around 62 images. Google and Amazon are actually pretty close, which is what I would have expected when I went into the study, about 39 to 43. So, with that, the final thoughts are that essentially when we benchmark all four, we found that our precision is 85%, and we found that when we build a specialized AI, we're about the same in terms of image accuracy between real world and internet-based images, suggesting that our ML layers on top of deep learning, which is somebody mentioned before, like an ensemble, kind of like gave the best result, and that deep neural networks do outperform traditional approaches, but can become biased if not trained on real-world data. So be careful whenever you build your models on ImageNet or any kind of like curated libraries. And some of the future works, some of the people here earlier were talking about like speech and nutrition. We're working on that too. Like we're trying to process about 30-second audio files from iPhone or Android voice recording feature based on like data sets as well as different languages. And we're trying to detect food labels. And this was an earlier question that was asked: why, when Google Assistant just works or Siri just works, just translation, what's the need for another artificial intelligence? Well, the need is basically, if you say I ate a large cheese pizza, large is now a word that we have to key in, but if you just said I had eggs and bacon or something, then we can just do a simple dictionary search saying this is a food or not. So there's some caveats here, and that's what they meant by like understanding the word is more important. And of course, text to nutrition, we can try to leverage NLP to detect food labels, and the same thing happens here, because you can't just do a simple dictionary search. You gotta understand what the user is trying to say here. What does I ate little mean? You know, stuff like this. Image to nutrition, we already have it working, but our goal is to reduce the cost by running on dedicated hardware, or, this fellow, I can help here. So, because the accuracy is there, but at the cost of, running all these networks all the time, dedicated. Because you can save costs by, after a year or so, when it gets to the steady state, but until then, you'll have to eat up the cost in order to deploy your deep neural network. And the point to take here is AI with the help of deep learning can provide the technology needed for us to live a healthier life.
Thank you, Adit.
Questions?
So, what is the data that you guys use to train these studies?
So, that's a good question, because I mentioned ImageNet. We kind of use ImageNet to train, and then when we're trying to run some of the ImageNet data, just like Google or anybody else when they start, we started bringing WordNet into its play also. And then we built some additional ML layers, and we knew food is not a, so if I were to a drawing board, I had one of these Andorin classes where he would just go on a whiteboard and explain suddenly. So it was like only 100 people, and you just do that. So if imagine a whiteboard here, right? Your simple classification problem would be like, I have triangle, square, and circles. Like it could be classes of wines, like Merlot, Cabernet, Syrah. And if I plot them on a graph, I can do an SVM or draw some lines and say, with this line, I can clearly separate and say, you're a triangle or not a triangle, which means I can say you're a Merlot or not a Merlot. And I can do the same thing. But yeah, so in 3-dimensional, 4-dimensional, I can do that, or just wines, I can do that. But when I'm talking about food in general, the space is so vast, like you basically have to train on that whole data set. And you're going to get values back from the ImageNet, and then we rewire that up with WordNet and see which subgroup you belong to. For example, like if you got pan, there's a possibility, and because these are CNNs, right? So you might scan eggs and bacon, for example. Or eggs and pancake is a better example because it's actually happening. You scan eggs and pancake. Pancake sometimes looks like a cheesecake, so you're going to get cheesecake, pancake, and eggs back. Okay? But if you look at it in WordNet, eggs and pancake will be under the subgroup breakfast, whereas cheesecake is under subgroup dessert. So when you do the subgroup level, you can then say this is most likely a breakfast item, not a dessert. So you can drop all the other labels. So you'll have to build an ensemble like this in order for you to achieve.
And do you guys attempt to do any transfer learning on ImageNet, like just taking probably the ResNet architecture and doing some sort of transfer learning on just for the food and see whether it improved the performance of Google? The regular thing, because sometimes just plain transfer learning helps, right?
On top of Google, you're saying take
on
Google's
top of
data.
some ResNet or something, just some transfer learning with the specialized food data, just to see that the labeling is accuracy.
So basically, like I assumed actually Google actually did the net infrastructure, or even AWS recognition. But you saw so one thing you'll notice is we got more images right compared to those services, right? And that means immediately, even though we started ahead of time, one of the reasons for the first study was to figure out, hey, should we just drop it and should we just use them? Because they're underlying already using neural network with lots of layers to make their model, right? So, and then it turned out, no, we shouldn't, because it's agnostic and it's going to miss out on labels. Like what I'm saying is I can only at most get as accurate as Google, right? We never filtered out all the labels. We used all the labels that Google gave. So in a real application, we can't throw 100 labels at your food and ask you to say which one's right. So what I meant to say quickly for that one was what ended up being better is boosting by hitting local data sources. And maybe if that didn't happen later, you can answer any question.
So using your WordNet, can I ask?
Yeah, okay.
Using that WordNet layer, can you easily identify between like New York style pizza and Chicago style pizza in your?
Yes,
Okay.
you can, but there's a little caveat because like, you can't do the subgroup strategy there because it all goes to dishes, but like underneath dish. But yes, the point is, so you'll see this sometimes in deep learning practices. You'll have, again, I wish I had a whiteboard, like Andrew will explain, sometimes like you convolutional neural network is to get all the common labels, right? Then you need to go specific again, because this is what I call in studies deconvolution. Because you're going from, hey, it's a pizza, to now figure out what type of pizza it is. That's called deconvolution. That's against actually like CNNs. So then you build your random forest, etc., to go and get specificity.
Yeah, so we know facial recognition is very famous. If I feed a photo of a person, if the machine probably will try to determine who that famous person is.
Yeah.
But what if I'm not asking him to tell me what the person is? I want him to tell me like what shirt the person is wearing or what watch the person is wearing. Is there a way to select certain part of the picture and feed it as input?
That's a good question. I mean, I have, like I think data science is very domain specific too. I'm pretty sure a data scientist in that domain could possibly tell you the answer, but if I were to approach it, I would do it domain agnostic first and write machine learning algorithms on top of the labels generated to cut out everything that's not related to clothing. So that way, you can build your open architecture, which is already like your resume, these architectures are already there. You're going to get thousands of labels, right, from your, right? And then you can just use your ML based on database of clothing. I'm pretty sure there should be many databases for clothing, and make sure you take it from all across regions of the world, and then build your ML layer. Because now you know your feature space. Now this is a machine learning problem. It's no longer a deep learning problem. So reduce the problem space a bit, and then approach it that way.
Thank you.
So, did you have to use any GPUs for the training? If not, how long did it take for the training?
We did. So we ran completely on the data. So at that time, we were debating whether to use H2O AI, Spark Lib, or anything else to build an AutoML to kind of evaluate. At that time, basically Dataproc came from Google's infrastructure and was much easier. It uses Apache Beam, and that infrastructure is, in my opinion, if you're starting now, don't start with Spark. Just go with Beam, because you get real-time and batch-based model building. And it's on the Google's infrastructure. It's pretty easy to set up Apache Beam, so we just did that on that infrastructure.
So how long did the training take?
It took about a week to 2 weeks to train all the data. But then what will happen is every time we train the data and we have like a new data source that we want to hit, we would update. And there's methods of doing partial updates instead of retraining from scratch. For example, like we would bring iteratively, I mean this entire project for like 2 years. It took about 2 weeks to full train on the ImageNet. And after that we kept building iteratively every week. We added like first a data source for Chinese cuisines, then we had a data source for Japanese cuisines, etc. to build on top of the ML layers.
Any more questions for him? Very good, Aditya. Thanks a lot.